In this lecture, we continue our study of countability of sets. So last time we have defined what is countability of a set, and also we have given an example, that is the set of all integers, that is Z is countable set. Okay, so our goal of this lecture is to generate examples of countable sets. The outline of this lecture is sequence and countable sets. So here we study the relation between sequences and countable sets. Next, we prove two theorems. In the first theorem, we show that infinite subsets of countable sets are countable. In the second theorem, we show that countable union of countable sets is countable. So let us begin with the first item, sequences and countable sets. So sequences and countable sets. So let us define what is a sequence. So definition: a sequence f is a function with domain set of all natural numbers. A sequence f is a function with domain that is on the set of all naturals, where n equal to the set of all naturals. This is equal to 1, 2, and so on. So, for example, if from n to set of all reals, so this is called a sequence of real numbers. Okay, so this is a real valued sequence. Or one can say that a sequence in R. Set of reals. And more generally or similarly, if X is any non-empty set, then a sequence, that is a function f from n to x, this function f from n to x is called a x valued sequence, or a sequence in X. Or a sequence in X. So we have some notations. We denote a sequence. We denote a sequence f from n to x. So x may be a set of integers or set of rationals, or set of reals, set of complex numbers. So x can be any non-empty set. Okay, so if we denote a sequence f from n to x, so x valued sequence, or a sequence in x, by xn, n belongs to set of naturals, or in array x1, x2, and so on, where So what are these xn's? So xn equal to f of n. Okay, so these are called terms of the sequence. Terms of the sequence f. Also we may say that so f is a sequence with terms in R. Okay, the first example here. Well, so these terms xn or x1, x2, x3, and so on, these need not be distinct. So we have remarks the terms x1, x2, and so on need not be distinct. And second remark is we may regard a countable set as a range of sequence of distinct terms. We may regard a countable set as a range of sequence of distinct terms. So this is a new word. What is range? So if f is a sequence into x, then f of n such that n belongs to set of all naturals. This is the range of the sequence f. Or if you denote this sequence by xn, n belongs to set of all naturals. So range of this sequence is range of this sequence is the set xn such that n belongs to set of all naturals. So this is called range. Okay, so let us discuss a bit the second item in this remarks. So note that if x is countable set, so by definition x is equivalent to set of naturals. That is, we have a bijection from n to x. Let's say f is bijection from n to x. Okay, so this is bijection, and this is also a sequence, and this is bijection means f of n, this is equal to x. So range of and this is equal to f of n, where n belongs to set of all natural numbers. Okay, so this is nothing but range of this sequence, and which is equal to x. That is, and this sequence uh, has distinct terms. Okay, because this is bijection, and in particular this is injective. Okay, so we may regard a countable set as a range of a sequence of distinct terms. Okay, and furthermore, converse of true is also true. Furthermore, the converse of true is also true. So that is what is converse. If you can write the elements in X as a as a range of a sequence of distinct terms that is like this: x1, x2, and so on, where xn is not equal to xm for all m not equal to n in set of all natural numbers. Then, okay, so this is m. Then x is a countable set. So we have, then we will have bijection f from n to x defined by f of n equal to xn. Okay, so the converse is of 2 is also true. Now we have an exercise here. Let xn, n belongs to set of all natural numbers, be a sequence of real numbers. Be a sequence. So this is exercise 1, sequence of real numbers. That is, the terms of this sequence are real numbers. Now show that it admits, the sequence xn admits a monotone subsequence. Yes, so this is the exercise. Now we move to the second item of today's lecture, that is theorem 1. Now we state and prove theorem 1. So let us prove theorem 1. Let us state theorem 1 formally. Theorem 1. It says that every infinite subset, every infinite subset of a countable set X is also countable. Let's prove this. Let that E subset of X be an infinite subset of the given countable set X. So this is X is given countable set, given countable set X. So what to show? To show E is countable. The proof is constructive. So basically, to prove that E is countable, so we have to give a bijective function from the set of all natural numbers to E. So by second remark and the hypothesis X is given countable set, so we can arrange the elements of X in a sequence of distinct terms. Okay, so arrange the elements of X in a sequence of distinct terms. Like x equal to x1, x2, x3, x4, and so on. Let's say this is xn, and so on. So we arrange the elements of x in the sequence of distinct terms. Now we construct. Now we construct a sequence of natural numbers. A sequence of natural numbers, that is sequence of natural numbers which is in k belongs to set of all naturals. That is, for every k in n set of naturals, so that is, let me write, for k belongs to this nk, this belongs to in set of all naturals. So now we construct a sequence this inductively. Yeah, let me write here. So now we construct a sequence of natural numbers this inductively as follows. Next slide. So what is n1? So this sequence is like n1 into n3 and so on. This is the same as n1 into n3 and so on. So this is n1 first term, into second term, n3 third term, and so on. Okay. So what is n1? n1 is the smallest integer. n1 is the smallest integer such that xn1 in is the smallest natural number such that n1 xn1 belongs to E. Now we, let's say, chosen n1 and so on in k minus 1. Now we choose nk. Now nk is the smallest integer such that, or smallest natural number such that x nk belongs to E minus x in 1 and so on, x in k minus 1. And because E is infinite set, so if you remove finitely many elements from E, then it will remain infinite set. So this is, in particular, this is non-empty. E minus this finite set, this is non-empty, so there exists. So x and k belongs to this, where nk is the smallest natural number. So in this way, we construct sequence inductively. So now we define, finally we define a function f from n to e by f of k, this is equal to x n k. Okay, and this is bijective, and hence by definition E is countable. Okay, so before going into the second theorem, we have an exercise. So this is exercise 2. Let me change the color. Let A be a set such that A is equivalent to B for some, what is B? For some, for some countable set B, which is subset of set of all naturals, then show that A is also countable. So now we are ready to state and prove theorem 2. Here is theorem 2. Let us state the theorem formally. Let En, where n belongs to set of all naturals, be a sequence of countable sets. That is, for every n in the set of all naturals, En is countable. Okay, so let this be a sequence of countable set and put S equal to union En. N belongs to set of all naturals. That is, S is countable union of countable sets. Then what is the conclusion? Then the conclusion is then S is also countable. Also countable. So if now we prove this. So because En is countable for every n belongs to set of naturals, in particular, let's say, so this E1, this is countable. So we can arrange the elements of E1 in a sequence of distinct terms: x11, x12, x13, x14, and so on. And similarly, we can arrange the elements of E2 by x21, x2, x23, x24, and so on. Similarly, this is E3. This is equal to x31, x32, x33, x34, and so on. And E4, x41, x42, x43, x44. Now you can Now we define, so we can, so similarly we can arrange the elements of E. I is for every I. Okay, so therefore if x belongs to S, then x belongs to some E I. For some I belongs to set of all naturals, and then x equal to xij for some j in the set of all naturals. Now we define, f from S to set of all naturals by f of xij. This is equal to 2 power I and 3 power times 3 power j. Okay, and it is easy to see that this function f is injective. So f is injective, and this implies if you restrict the codomain f from S to f of S, this is the image of f under the function f. So this is injective and surjective. So this is bijective, and let's say this is equal to B. So if from S to B, bijective, and note that B is infinite subset of set of all naturals, and set of all naturals, this is countable set, so B is countable. That is, B is countable, and this is bijective. So S is equivalent to B, hence this implies S is also countable. So we stop this lecture.